So don't worry, but this is recording. However, I do want to share a website or YouTube if I haven't already done so. So I do have a chapter 5. I have a really good video of everything that I'm going to cover today. I covered in this video on YouTube, and I'm going to go ahead and post it on our page here. So we have our inside of general, inside of MAE 330-11, we have our chat that's associated with this video. I'm going to go ahead and post it there. And then send. Okay. So there it is. Make sure I'm sharing my desktop. I think I am. Okay. So I posted a link to a chapter 5 video that I should have put something on there. This was. You guys, so we'll probably have time to cover it, but like in my last class, I ran out of time, so I'm going to ask people to just look at it. We'll see if we even have time to go over example problems. It's pretty dry, this chapter 5, but I'm going to do my best to give a good lecture. All right, so a little bit of background on this chapter 5. Let's see. Hold on a second. All right. So a little bit of background. So this is chapter 5. And we just have it, we call it control volumes. But what's the other title associated with it? Just to make sure, let me see. It is, just want to capture the complete name of the, control volumes. And then we can just say mass and energy analysis of mass and energy analysis of control volumes. All right. So up until this point, this will be the last chapter where we're dealing with the first law of thermodynamics. Starting chapter 6, we will be transitioning to the second law of thermodynamics. So things get a little interesting. Mathematically, I think chapter 5 is more intuitive, and it's a little bit, but once we get into chapter 6 stuff, it gets a little bit weird, as the second law of thermodynamics is not as it's almost like there's a little bit of philosophical part of chapter 6 of looking at the second law. So to summarize this chapter here, it's the first law for control volumes. All right, so if you don't remember the first law, you might want to go to our chapter 2 lecture notes to kind of familiarize yourself with it. But we'll explain a little bit right now. So I'm going to go ahead and draw. We have a tank. All right, so one thing I did tell the other class is that this lecture, well, I'll tell you guys later. But this lecture that I'm giving right now, I gave to part of it, and this was like 3 years ago, I gave it to a bunch of professors at Cal Poly University or Cal Poly in San Luis Obispo, as I was applying for a permanent tenure track teaching position there. So I might as well share. The funny thing is that I work in a really good area right now, and I get to design spacecraft that goes into outer space. And not only that, I work on cool projects. Right? So for JPL, for the 13 years I was there, I worked on Mars projects. I worked on the Dawn project. Was the we sent the satellite to a dwarf planet called Ceres, and I operated the satellite. So I was there in the operation crew. So I got to do a lot of cool stuff, right, throughout my career, and I really enjoy the work that I do. But I always had this itch to teach full time. Now I like I like teaching, right? I feel that for me to do a really good, thorough job of it, I would love to teach full time because, right, my day job is to do. So I know it sounds weird because some people are probably thinking, yeah, but I work in industry, so bringing industry to the classroom is a good thing. It is. However, like helping students, it's more of a full time thing, and but anyway, so that long story short, that other class that this presentation I gave, so I didn't get the teaching job. This is 3 years ago, and there's a story behind this teaching job that I'm giving this lecture because I had to prepare a lecture, and I had to do a mock lecture for students, but there was professors there, and they got to see how I operated, how I gave a lecture. They tend to do that with faculty that are hiring or looking to join them. So and I thought the presentation went well, except there was a lot of problems with it. So for one, so I come into, they told me, okay, prepare a lecture, and I said, okay, I'm going to do it on control volumes, chapter 5. Well, they use a different book, but the guy I was talking to knew was a thermodynamics professor. He said, control volumes, are you sure? Are you sure you want to touch that subject? I said, yeah. He says, very mathematically intense, he said. And the professors, you may set yourself up for, getting a hard time, right? So some of the professors, they may push you on certain things. And I said, that's fine. I don't care. This is a subject that I like and I feel comfortable teaching. So anyway, so I taught it, and then the room that I was in turned out was a chalkboard. There was no whiteboard. So in my 14 years teaching at Cal State Long Beach, I've never taught anywhere besides a white with markers, right? And this was a chalkboard. So I'm like, and then when I was using the chalks, it kept cracking and breaking, right? And so it was embarrassing, and it's writing on a chalkboard is different, like in terms of how, the cadence that I have in terms of writing. Even just writing here on this tablet, it's hard, right? It's different, so you get used to it, but it's taking practice, right? Because writing on a whiteboard, you get used to it, right? And I used to be able to write really fast. Well, writing on the chalkboard, it's there's friction, and it's different, so it's slowing me down, and I ended up having a pretty miserable presentation, though I think I gave a good one. And then I got a hard time. There was a professor giving me a hard time there, and he was a professor. I used to go to that school, so 30 years ago, and he was the same guy. 30 years later, here he is. He remembers me, and he gave me a hard time. So anyway, long story short, I didn't get the job, but we still keep trying, right? Never give up. So, and besides, I like what I do in my day job too, so I can't complain. All right, so this is the first law of control volumes. All right, so what we've done up until this point is we had a box and we had a control surface, right? So this is the control surface here, CS, or AKA if it's for the actual surface encompasses a volume, the control volume. So, but this is the first time we're introducing mass coming in, and mass or like a flow. So there's energy associated with flow. There's the mass energy associated, the fact that there's mass coming in. If it's, for example, a high velocity, well, there's going to be energy associated with that. But there's also pressures associated with it. It could be kinetic and potential energies. So we're introducing a new area of energy. So let's go ahead and I want to talk about mass conservation of. So the conservation of mass is a little bit like the first law. The first law is conservation of energy. So don't get that confused. Conservation of mass is very similar. It tells us basically the mass that comes in. So let's go ahead and write it. So the mass that comes in minus the mass that leaves a control volume or crosses through a control surface is equal to the change of mass of the control volume, right? Which is, again, M2 is mass that comes in, mass that comes out. One. All right, and this is and the units here are in kilograms. Okay, I got to drop a box on this. This is the conservation of mass. It's a lot like the conservation of energy, but it's now mass that we're looking at. Follows the same law. All right, so if we say that, so this is, again, just going to write it here because I'm going to write it again in rate form. So I messed up here. I don't know why I put a 2 there. This is 1. All right, so so we're recording, so you guys know. Now let's do rate form. So if we wanted to look this in terms of differentials, because we want to create a differential equation. So I want to write dmCv is equal to the differential of the mass that comes in. So this is 1 dm2. This is a 2 minus the differential of the mass that comes out. Now in rate form, which means now we're looking at as a function of time, we say that dmCv dt is equal to d dt m. I'm going to say, instead of 2, I'm going to say n minus d dt m out. All right, and so now I'm going to say that there's another way I can write this. I can say, well, the rate of mass that comes into the control volume as a function of time, I'll put that in parentheses, is equal to, instead of writing ddtm in and ddtm out, I'm going to say is m dot in and m dot out. So what it's telling me is that, so this is the total mass coming in terms of, and the total mass coming out in terms of kilograms, but I could also say that the mass flow rate, m dot in minus the mass flow rate that comes out, is equal to change the mass inside the control volume, the rate of change of mass in the control volume. So if this was steady flow, in other words, if the mass that comes in, the mass flow rate that comes in, and the mass flow rate that comes out are the same, then the rate of change is 0. So if it's not steady, if more mass rate coming in is if it's coming in larger than what's coming out, then it accumulates mass, right? So then this becomes positive. This dmCv dt becomes an accumulation rate. Vice versa, if the mass that comes out is like a drain that's coming out faster than what's coming in, then this dm dt mc is negative, right? We're losing mass as a function of time. All right, so I'll go ahead, and the units here is kilograms per second. Go ahead and drop a box around there. Sorry that I'm encroaching on the other problem. All right, so that's the mass, conservation of mass in rate form. Now let's look at this. I'm going to have to draw a new page here, just so I can have plenty of room, because this next bit is a little bit large here so we can see everything that's going on. I'm going to go ahead and draw a box. So let's look at this box a little differently. All right. So I'll draw a nice big box, and then I have an entrance, just like the previous one, and an exit. All right, and so I have, just say, an opening and an exit. Okay, before I continue, I forgot to mention, I mentioned in my other class. So I do talk a little bit about, I like, careers and stuff like that, but I don't want to talk too much about it, but I did want to mention that I mentioned my wife's company, Chevron, is giving a presentation to the College of Engineering, right? So this is a virtual presentation. I think you guys might have gotten emails on it. So they will be giving a presentation on next Tuesday, the 13th. I just don't have the time and the details. Um, I don't know if my wife's going to be at that presentation. I think she is, but she's not giving it. It's her coworker, um, Eileen, I forgot her last name, but she really nice lady here. She's a Long Beach native, and she's going to talk about Chevron and what she does there. And so again, if you guys are interested, attend that, and it's always good to check it out. And if there's any questions, and if you have any questions, post the questions to her. And it's a good opportunity to get yourself out there in front of recruiters. And so anyway, so look out for that. If you don't have that information, you can email me or chat me here on Teams, and I can get that information as to what the Zoom code is and all that, what time it is. Okay, so back to our problem here. So let's look at this box. We have a control surface, just like last time. It's designated by this dotted line here. See how good I am and how quick I am at drawing the dot. All right, so anyways, you guys get the point here. This is just signifying our control surface. So this is, I call that CS, is the control surface, but it's also, that's just the surface that encompasses the control volume. So let's look at this a little differently. Maybe I should have made this a little bit. Here, bear with me. I need to make this a little bit bigger because I ran out of space the last time I tried it. All right. So let's go ahead and make this opening a little bit bigger so you can see what's going on. All right. So let's pretend or assume that we have some fluid that's coming into the control volume. So it's a slug of fluid. We'll call it blue, just like pretend it's water or something. Now there's a volume associated with this fluid, and hold on a second. I wanted that to be blue, but I wanted to go to a pen now, and I want that to be black. All right, so this is a differential amount of fluid coming in, right? So we're going to call this dV. Now you'll see that I'm using V with a little line at the bottom to designate D volume, right? And this volume has a pressure associated with it that we call P, and a mass that we call dm. So it's a differential amount of volume that has a differential amount of mass, dm, and a P for pressure. Okay, now let's assume that there is a certain, so there's the fluid that needs to get through that control surface, but since there's already fluid there, and so they just say to get this fluid in, we got to push it through. So I have this little surface there, and I'm going to say that the area of this, so okay, the area associated with this area here, we're going to call dA, right? And the force here to push it through, we're called dF. So the force required to push this through by crossing the control volume or the control surface is dF across an area dA, and the distance here to push it all the way in we'll call dx. Now let's go ahead and write down what we see here. So we're going to keep track of the mass this way. The mass is going to come in here. It's going to come out the back. So we're going to say that dV, right? We know that dV is equal to an area times the swept distance, right? So the area times the distance is will be the volume, right? So we'll say it's dA dx. That's the differential volume. And now if we were to do this in rate form, so we want to do a rate, because we eventually want to get into flow rates, right? So we say that in rate form, we say dV dt is equal to dA dx dt. So we're only giving dt to the things that change as a function of time. So we know that the volume changes changes as a function of time. The area does not. The area is constant, but we know the distance changes as a function of time. And we know that this means, so we know that dA, we can represent this dx dt. We know that that's a velocity, right? So it's the change, it's the rate of change of distance over time. So we call that v, and we'll put an arrow over it so that there's no confusion. That's the normal velocity through the control surface. So that's not volume, it's velocity, right? dx dt is velocity. So let's keep that in mind for a second. We're going to use this part later. Now let's say, all right, so this is the mass flow rate, or this is the flow rate, or the change of volume as a function of time is equal to the dA area times the velocity of the fluid. Okay, very good. Now let's go ahead and say this, the differential mass, right? We want to give it a dot. Say the flow rate coming in is equal to so the flow rate is equal to the density times the volume, right? So density times volume will give us m dot. So or the I'm sorry, the volume flow rate. So the volume flow rate is actually dV dt. So let's see, I think so that was the volumetric flow rate we just found up there. So density times volumetric flow rate. So we, instead of writing density, we're going to say 1 over the specific volume, dV dt. So the volumetric flow rate times 1 over the specific volume is equal to the differential of the mass flow rate. All right, so now let's substitute for this. So we're going to go ahead and say, what are we going to do? So we're going to say dV dt is equal to this here, right? Which is dV dt is right here, right? So we're going to substitute this. And we're going to say that dm dot is equal to density dA Vn, the velocity. So dA V sub n is the velocity, which is equal to 1 over the specific volume dA V sub n, which is the velocity. So I'm going to box that. That's how we relate the flow rate with the velocity. All right, so we still haven't got to the force yet. So what's this force vector here doing? We want to find out. The goal here is to try to integrate into our first law equation the energy associated with the mass of fluid coming in and out, and the energy associated with it. So the energy of the mass and the energy of the fluid itself. So let's go ahead and continue. So now we're going to say that we know from the past that, sorry, go back to my pen, that the differential of the work, for example, the boundary work, was equal to force times the distance, right? dF dx. So we're still in differential form here. So I say the differential of the work is equal to dF dx, force times the distance. And we're going to say that instead of saying dF, we want to put that in terms of pressure. So we say it's pressure over times area, dA, times dx, right? So that's our dw. Excuse me. And then we know that area times the distance, right? Like we did up at the top here, is equal to a volume. So we're going to say that this is P dV. dA dx is equal to dV, just like we did up here. All right. All right. So so that is our. That's how we. This is how we. This is our flow work. This is what we call our flow work. And it's a little bit like it is a little bit like the boundary work that we were talking about, but this is associated with the flow. So this is the work associated with the flow and the flow work. Now, oh gosh, can't draw straight. Anyway, I won't underline that. So that's the flow work. Now let's get the rate of the flow work. So we're going to say dw dot is equal to, we're going to say dw dt, which is equal to pressure dv dt, which is equal to pressure. And we're going to say, instead of dv dt, we're going to say this is specific volume times dm. Right. So that you go to the previous page, and this you'll find out how we substituted in dm dot, right, times pressure times the specific volume, right? So you can do that if you, and therefore we're going to say, we're going to box that in, but we're going to say dw dot is equal to p v times the mass flow rate dm dot. I'm going to box that in because it's important for us. So this relates the flow work to pressure times volume and times the flow rate. Okay, let's see if I can expand this. Yeah. All right, so I didn't say that this is, so this is where it gets pretty math intensive, because at the end I want to show you the equations. I could have just jumped to the equations of how we calculate energy of a control volume, but then, you know, you would be asking me, well, where'd this come from, right? And this covers that. Okay, so let's go back to the first, right, from right here, I'm going to draw a line. And I'm going to say, let's go back to the first law. What do you guys remember of? This is the first law for closed systems. For closed systems. So you guys remember that, right? That the first law for closed systems looks something like this. The rate of energy of the system has a function, the rate of energy with time is equal to Q dot minus W dot, right? So remember, Q is the flow of heat coming in and out, and W is the work coming in and out into the control volume. So this was a chapter 4 stuff, and this was for a closed system. So now we have to use this, to this equation, we have to add the energy associated with the flow, right? So we did all that right now. So I'm giving you all these differential equations to do that, but now we got to start piecing it together. And let's start off by saying that the energy rate associated by that crosses the control surface is equal to the mass flow rate that crosses the control surface times, remember, EMEC. This is the energy associated with, it's the energy of the fluid crossing the control surface. Remember that EMEC is composed of a lot of different things. So we know that this is m dot that crosses the control surface times, and then you guys remember that this is, there's U in here, plus there's kinetic energy that crosses the control surface, plus potential energy that crosses the control surface. Is that everything? Yeah. So that is the energy associated with everything that crosses the control surface. And then, right, we're going to use little symbols here to represent what we mean by N And then for exiting, we're going to use E, and that's going to mean exit. So now we can go ahead and say the first full law. So the first law now that has everything to do. So basically, what I just drew right here for the chapter 4 closed systems. Now we're going to add the flow rate at work. Let's go ahead and say d e of the system dt. Am I still on a? Yeah, okay. Is equal of the control volume. So that is equal. So this now is pertaining to a control volume is equal to Q dot minus work dot. Now there's more stuff we got to add. Plus M dot, the flow rate that comes in times the energy of the flow that comes in minus the flow rate that exits the system times the energy, the EMAC of the fluid that exits, plus now we're going to say M dot times the fluid that enters times P I little vi, and then we're going to say minus M dot E P E little ve. All right. So you guys remember up here is where we talk about P V DM. This is the again, this was the flow work up here, and that's associated with the flow work there. So let me box this in. All right. So this part here is associated with the, let's see, which was the part here. Let me draw a line there. No, I'll underline it, something more noticeable. So this is a part associated with the flow work, right here. And in green, this is the part here that's associated with the energy, the E mass. So did I write that? Yeah, it's right here. So it's here. It's basically this part here. So in orange, it's the flow work. And the green is the energy of the mass. So the energy of the mass is, right, if you have a high velocity fluid, there's kinetic energy there. If you have a fluid that's like coming down a hill or something, and then there's a distance associated, there's potential energy associated with that. Okay, so I'm going to start a new page here.
Professor, could you say that one more time?
Okay.
I'm colorblind, so in the different.
Oh, yeah, sorry about that.
Okay.
So yeah, so let me explain this. So what I have here, let me go ahead and stay with one hash. This is a part of the equation that has to do with the energy of the mass, right? And what I mentioned is imagine the mass that comes into the control surface that punches through. So if I was to go, let's see if I can scroll up, that blue part there, that fluid that comes in, imagine that's like a bowling ball, right? So it's kind of like the mass, it's the energy of that bowling ball going through the tank, crossing the control surface. That's what's in with the single hash there. And here with the double hash, so I'll just change it back for the double hash is, I didn't mean to do that. Okay, it's this one here. So it's basically, this is the work, this is the flow work, right? So we have the two, so what we added to the chapter 4 closed system, now we're adding the energy of the mass flow rate, and then there's the energy of the flow work, which has to do more with pressure volume. Okay? All right, cool. So let me go now back here, and let's continue this discussion. All right, so it would have been nice to have that. Let me see if I can come back and go to the previous page and copy that equation, because we're going to refer to it right now. Let me go ahead and select that. Paste it to the, paste it up there. Okay, so now let me go ahead and explain some more. Okay, good. So the end goal is to give you an equation that's simplistic, because this is actually going to get worse before it gets better. And let me explain. Because we need to include enthalpy here. All right. Or else it's going to get out of hand. This is the enthalpy term is going to get rid of our PV and our U terms. You guys remember that from last time? So the way we're going to do that is we're going to collect these terms here. So there's the mass that comes in. So we'll put that at m dot here. The flow rate that comes into the system, EI, plus mi dot pi vi. We're going to call this pi vi. We're gonna treat that a certain way. So let's go ahead and the equation up at the top. We're gonna factor out m dot I. We're gonna say that is EI plus pi vi. And then we have to, instead of using E, we have to associate the mechanical energy associated with the fluid. So we're going to say that is m dot I again. And now we have to start everything that's associated with the letter E. That's UI plus KEI plus potential energy EI. And then we're going to throw out here, just in case we didn't cover everything, there might be energy associated with something else, like electric work or something like that, okay, that we didn't cover. Plus PI VI, all right. So that's the complete E term here. So I don't want to, but this is basically this guy here, right? That's what we went ahead and just converted into U's and KE's and PE's to give a complete picture. All right, so it got ugly, right? I got, just as we were thinking we were going to get the nice equation, it got a little ugly. So but don't despair, because what we can do is we can collect terms. We know that enthalpy, that thing in the back of the book that you use to determine how much energy it takes to evaporate water and such. We know that that term is equal to UI plus PI times little vi, right? And therefore we can start, thus, we can go ahead and collect terms, and we can say, now, this part here, we can just say this becomes mi dot, and it becomes hi, and it's the other terms that we can't neglect: kinetic energy, potential energy, and then this other one that we say E other, just to, in case there's other things out there that are part of the energy of the fluid. All right, very good. We're doing good here. 7:42, got good time here. All right, I'm getting to the end here. So then we say, then the first law for control volumes. Now we have a first law for control volumes. We expanded from the first law of closed systems. Let's write it out. The rate of change of the energy of the system as a function of time for the control volume is now equal to Q minus W. And now we have all this other stuff, right? That has to do with the mass flow rate. I times, and then it's HI plus KEI plus PEI plus E other I minus the flow that exits, and same thing, HE plus I'm sorry, yeah, it's HE plus KEE plus PE little e plus E other E. All right, so that is the complete system. Maybe put that in nice and red. So this is the equation you use to to do all the calculations from here on out for chapter 5. So obviously stuff falls out, and there's a little bit more simplistic way of doing this. But let's go ahead and continue a little bit. It turns out that this is as far as I got in my other class. But typically in this class, I fall behind. So it wouldn't hurt to catch up a little bit. Let's see, it's 7:44. So, I typically like to go an hour. So let's go another 15 minutes and then we'll call it a day. Let's see if we can just expand this a little bit instead of going with it.
Professor, I have a question.
Yeah, yes.
So the kind of parenthesis that you do between dE system over dt and CV, is that parenthesis part supposed to mean anything or no?
Oh, you're talking about here?
The curve part between dE over dt and CV. Like, I'm just wondering if that makes if that's supposed to be important.
No, it's just saying applied at the control volume. Okay. So as opposed to the closed system, the closed the closed system was chapter 4. So as opposed to that, now we're applying it to the control volume. So yeah, it wasn't meant to be anything like an operator, a mathematical operator or anything like that. So now there's ways of simplifying this, right? Obviously, if we neglect, but we can't always do this. So this is just for, I say most problems in this chapter, we can, so if we can neglect, right? So if we can neglect potential energy, right? KE, PE, and E other, then this breaks down, because we're neglecting kinetic potential. Now this might be confusing a little bit, but we can say du, capital U, dt, and I'll explain right now, of the control volume is equal to, we still assume everything is happening in terms of heat loss, work, and now we have the terms that have to do with the flow energy. It's m dot I h I minus m dot E h E. All right, so the reason that we put a U here is because the energy is now exclusively, instead of where it was U, whenever we get rid of KE and PE and anything else, then it just becomes an internal energy, right? It's the U component. You don't see this right now because there's an H here. It's enthalpy because it also absorbed the PV part. So I don't know if that's up here. I know it's, yeah. So we absorb the, I wish there was a pointer or something because I know you guys can't. But up here in the boxed equation, we absorb the PV and the U, right? So here, maybe it's up here, it's a little bit more clear. So in this equation here, we absorb, that I'm underlining right here, the U and the PV by just replacing it with enthalpy. So in reality, because we got rid of kinetic potential, this becomes an internal energy problem with pressure volume. So that's why we changed this to a U symbol. That's the only reason they went to a U. And I'm telling you this because if you go into, if you get into graduate work, you're going to see equations like this. These are basically the heat transfer equations, and or the mass, the energy mass equations, and you're going to see the symbolism. So it's just, I'm just telling you right now why you change that from an E to a U. And it simplifies it, right? And then now if this was a steady state problem, this du dt goes to 0. So now it doesn't become an accumulation of mass anymore, and now it's much easier to solve. So again, for steady state, I'm just going to put SS. We have we have d E dt, which is equal to du dt, which is equal to dm CV dt. All that is now equal to 0. right? So it's all 0. And so the left hand of the equation of the equal sign here becomes 0. And now you're just left with stuff that comes in and stuff that comes out. Instead, now the beauty with this now is that you don't have to worry about sign conventions anymore. And let me explain a little bit. So let me break it down, especially. I wonder if there's an equation that we use. So this can also be broken down. Maybe this is a good opportunity to start. Yeah, so this here, for steady state, so I'm going to say for steady state, I'll write it out. This will break down to, instead of saying Q, so we have that Q dot, right? What did we say? Q dot is equal to Q in minus Q out. I don't know if you guys remember that. And then W dot is equal to W out minus. So whenever we use this right here, whenever we did that, we assumed that there was already embedded inside of it was heat coming in, heat coming out, work coming in, minus work coming out, minus work coming in. All right. So if we do that, then we can go ahead and write this red portion here, this red bracketed dE dt goes to 0, and now we can, and if we replace Q dot minus W dot with Q in and Q out and work out minus work in, the problem becomes like this. Let me write it. Okay, Q dot in just gotta track my eyes here, plus work in plus, now I have to drop this term here. It's gonna seem weird, but it's basically a summation. We have to look at everything that comes in. Right now we've been looking at just a box with one inlet and one outlet, but we can have a box with multiple inlets and multiple outlets. So this is just to accommodate the multiple ins and outs. So we're gonna say summation of all the inlets, M dot, and we're gonna say H. And instead of kinetic energy, we're gonna say V squared divided by 2. Instead of potential energy, we're gonna say GZ, gravity times the height, is equal to, and we're gonna say Q out minus work out dot, I'm sorry, I said minus. I didn't mean to put minus. It's second. It's plus. So, and we can, so this is nice because now this just, as long as you put the stuff that comes in on the left hand side and the stuff that comes out on the right hand side, then it all works out. Plus work out. Let me see. Got to make sure I'm writing the right. Plus, we're all the outlets in this box. So we're going to say out, or should I say exit? No, we're going to say out. And we're going to say all the mass flow rates associated with the exits times H plus V2 square, or divided by 2 plus GZ. And all right, so this is an even more important equation because it kind of boils everything down. But I don't know if I can box this in because I kind of wrote it in as a slant. Darn it. All right, there we go. Maybe I can collapse this a little. All right, so very cool. Now, so this, let me explain this. All right, so now we can put things that are coming into the box. So if we have a box, a flow box, right? And now it can have multiple openings. So we can have, instead of one opening that comes in on here and one that comes out, right? We can have 2 that come in, and and one that come out, for example. So we can have right, a flow rate that comes in on the left here, a flow rate that comes in like that, and we can have one, or we can have 5 flow rates that come in and 5 or 3 that come out, right? So then this would be, so we're summing across what's coming in, so this can be like m dot 1, and this can be m dot 2, and then we can call this one m dot 3. So then the m dots on the left hand side, we would say this is for m dot 1 times h1 plus v1 squared divided by 2 plus gz1 plus m dot 2 times h2 plus v squared over v2 squared over 2 plus gz2, and then equal to, and on the right hand side we put everything that's coming out. In this case it's just 1, so this, we wouldn't need the summation, and it would just be m dot 3 times h3 plus v 3 squared divided by 2 plus z3. Okay, sorry. Whew. All right. So, and a lot of times we're neglecting velocity, we're neglecting kinetic and potential, so then it just becomes enthalpy. So in this chapter, for this chapter, enthalpy is big, right? And let's see, we got 5 minutes, and I would love to set up a problem, but we wouldn't go anywhere with it. But you know, so maybe I shouldn't. But maybe we can talk about a little bit about what this problem solves. We're going to use this to solve problems. I'll show you the following problems. It's energy analysis across problems that have flow rates. And so what are those kind of problems? Or what kind of components have flow rates in them? So the problems that we'll solve energy problems associated with the following components. So that would be, so nozzles, come on, right, so it'd be nozzles there, and diffusers. Diffuser is just a nozzle backwards. There's also heat exchangers, right? Because the heat exchanger has flow coming in, flow coming out, different areas where we might be exchanging from one fluid to another. Valves, control valves, flow valves, anything having to do with valves, pumps, turbines, mixers, like you have, like this is a mixer right here. Why? Because we have a flow rate 1 and flow rate 2. We're mixing them, and out comes a flow. So this could be your shower head, right? So your m.1 could be your cold tap, right? This can be your cold faucet here. This can be your your cold faucet there. This can be your hot faucet, right? And then here is the mixed, right? So do we have a mixed color here? No, we don't. So anyway, here would be, let's just give it a mixed type of color. So it'd be like that, like a mixed. So it would be some it comes in, here's the cold tap, the hot tap, this comes out warm. And you may have a situation where you need to find, okay, you want the water to come out at, just say for a shower you love, you know, just say 95 Fahrenheit. So then, you know, what flow rate of 65 degree Fahrenheit water with what flow rate of 120 Fahrenheit degree water would give you at the end 95, you know, a certain flow rate of 95 degree Fahrenheit water, right? And you can do that energy analysis with these equations here. Okay, so okay, that's all I got. Okay, Any questions?
Yes, Professor.
Okay.
So the equation you have up there,
Yeah.
I'm having a hard time understanding some of those letters in
Okay.
the equation. For example, the HI
Yeah.
and the one where it says plus E, is that other?
Yeah. So this would be, again, this is just these are general equations, so you have to accommodate. This was basically to accommodate all the energy associated with the fluid. So the way, right, this is basically E. So this would be, because this has an I subscript, this is just kind of a general energy of all the fluid coming into the control volume. And all the energy is there was the U and the PV, but we swallowed that up. We put that all into H. There's the kinetic, there's a potential, and E other is just to accommodate any other energy source that we don't have here. I had mentioned like electrical, but that would have been electrical would be accommodated with W. So, maybe I shouldn't have put E other there, but this is what the
it's cool. I just wanted to needed to understand what that one was because I got a little lost. So that makes sense though. That makes sense. Thank you.
So it's the energy. So for example, so some like say chemical energy or something that would fall into here, and then hit the chemical energy coming out of the box, right? So yeah. Again, this is when we start doing problems. It's not this complicated. So you'll bear with me when we start doing examples. But the equations you use all come from this. So when I took thermodynamics, our professor forced us to use these derivations. Before we can solve anything, he had us kind of calculate the derivations and write everything you see in red right here. We'd have to derivate this from the differential equations, and then we'd solve the problem. And I think that was like a waste of time. What I'm doing is, because no one does that, right? But it's better than just saying, okay, let's go to the page. If I would have just said, let's just go to page. So, okay, this is all nice, but I don't need to know all this stuff, right? I just need to get to the bottom line, and I got you to here, right? So I got you to this part here, and in reality, it gets even easier than that, right? When we start solving problems, they actually boil down to something more like this.
That's what I'm talking about.
Yeah, and you might have seen this before, right? But it all comes from now. It's not just one rate, one entrance coming in, one exit coming out, right? Sometimes there can be multiple taps, and so that's why you have to put that summation to include all the multiple taps of water coming in. So for a nozzle, you got one mass coming in, one mass coming out. But and for a turbine, but then you may have a mixer, right? You have several coming in and several coming out. You may have a mixing chamber with 5 flows coming in and 2 flows coming mixed. So then that's why you have to use that summation. And it really just comes down to this: everything that's coming in is on the left hand of the equal sign, right? M1 and M2, like I said. Everything coming out is on the right hand. This was simple because this is a steady problem, so that dE dt term falls out and it just becomes a simple equation here. So everything I told you right here, boils down to, right, this big equation boils down to this for the mixing chamber, right? Just this simple equation. But that's why I had to give you that, because then you might have a 4. So for heat exchangers, we have a flow rate we have 4 points, right? 2 points have flow coming in and 2 points have flow coming out. And then, so everything that comes in and out, right? Everything that comes in, you put on the left hand of the equal sign. So for example, what's coming in is the M.1 here, and then M.3, and that's on my left hand side. And what's coming out is M.2 and M.4. And it turns out that we neglect potential and kinetic energy, so therefore we can just have H. And here's your energy equation, right? Anyway, we'll do example problems, and hopefully I wouldn't call this the toughest chapter, but it's definitely the most computationally intensive one. Okay, And it does all. I mean, this is one chapter that I think if you got into any kind of fluid, heat exchangers, any fluid systems, you're gonna come back to this. So this will, like, I think I had a student at the last class saying, his teacher told him that 20% of what you learn in school you'll apply in real life. Of this chapter, if you go into heat transfer and anything we have to do with flow rates, you'll use 80% of this.
Professor?
Right. Yeah.
In regards to the presentation for Chevron, is there any
Yes.
way that you can just go ahead and post the Zoom information in the group chat? Just because I don't think I got any notifications for that, and I'm not sure where I'd find that information.
All right. Sure. Let me see if I still have my.
It's on Beachboard, College of Engineering.
Oh, really?
Let me check right now.
So if I go to Beachboard,
Down.
and if I go, I scroll down. Excuse me.
Can you
call
do all courses? I think maybe that.
View all courses. Oh, I have a lot of courses. What's the stuff I teach? So,
I don't think you have it, Professor.
because I have it as this is my instructor one, huh? They didn't invite me, so yeah. Okay, but if I go to Beachboard and if I go to, there's usually on the right hand side there's announcements and stuff.
Yeah, no, I found it.
Found it?
Yeah, I did. We have to register prior, right?
Oh, okay.
Yeah, so there's a link to register for it. And then
Okay.
when you fill out that registration form, it'll send you the information for the Zoom link.
Okay, cool. All right, so thank you for sharing that, because I thought, and I don't remember where I saw it, because sometimes I get it on, again, I think I got it on Instagram, because I follow the College of Engineering, and let me see if I could just check it, just verify. But anyway, I think I just got that link on Instagram, and but I tried to go to Instagram and I didn't. So there's a lot of industries, right? So coming and visiting. So one area is you might want to guys look into the Society of Hispanic Professional Engineers, Cal State Long Beach, because they keep a lot of tabs. They invite a lot of companies to come talk to them, and so they have a night with industry. I just see the information here, and it's October 16th, 2020, and I don't have that. Sorry. I mean, if I show you, you guys are probably going to be able to see it here. But just go to, the SHIP is the name of the club. Again, that's Society of Hispanic Professional Engineers at Cal State Long Beach, and they have a meeting, a night with industry, and that would be your opportunity to come in. Who's going there? Northrop Grumman, Boeing, Lockheed Martin. Yeah, they're all man, I wish Rocket Lab was going, but you know what? We're a little bit. Rocket Lab right now is just a little bit too kind of seat of the pants right now. But once we get a little bit more established, you'll start seeing us more involved with the schools. These big companies have funds already that are appropriated to do recruiting, and we don't, So I would love to be able to come down and represent like Rocket Lab or even NASA, JPL if I decide to go back in January. All right, guys. So I'll let you guys go. I'll be sticking around for a little bit if you guys have any questions. I'm going to go ahead and end the recording here.